Hello and welcome to the part 3 video of chapter 13. Today we're going to look at section 13.2, which is going to cover ideal gas laws. Now before we actually cover what the ideal gas law is, I wanted to kind of touch base on a few things that we've covered in class so far this year. If you recall, we have something called Avogadro's principle, and this principle just says that equal volumes of gases at the same temperature and pressure are going to have equal numbers of particles. We've talked about volume in moles. We know that the conversion is going to be 1 mole is 6.022 times 10 to the 23rd particles. And remember, particles could be like atoms, ions, molecules, and so on. We have what we call a molar volume. The molar volume is the volume that 1 mole of a substance occupies at 0 degrees Celsius and 1 atmosphere. Now, I did put STP in parentheses. STP actually stands for standard temperature and pressure. So standard temperature is 0 degrees Celsius, which if you recall, that would really be 273 Kelvin, and standard pressure is 1 atmosphere. So just know that you may see STP on some of your worksheets because that's assuming that you know that the standard temperature is going to be 273 Kelvin or 1 atmosphere. We have also done some work with Avogadro's number, and we know that 1 mole of a gas at standard temperature and pressure is going to occupy 22.4 liters. So we've used this as a conversion factor before as well. So if we wanted to find out the number of moles in, let's say, 3.72 liters at standard temperature and pressure, then we're going to take that 3.72 liters, multiply it by 1 mole over 22.4, and you can see, like, we should have had a liter here, but your liters are going to cancel out, and that's going to leave you with the unit of moles, which is what we want, and we'll end up with 0.166 moles. So that's just kind of a refresher on that. So if we look at an actual example now, example 5 says the main component of natural gas is methane, or CH4. We want to find the volume that 2 kilograms is going to occupy at standard temperature and pressure. So the first thing I have to do is I have to find my molar mass. I have carbon, and if you remember, carbon is 12.011 grams per mole, and I just pulled that right off a periodic table. Hydrogen is 1.008 grams per mole, but I have 4 of those, and I'm getting that from this formula right here. So if I multiply that by 4, I end up with 4.032 grams per mole. And if I add both of these numbers together, I end up with 16.043 grams per mole of methane, which is CH4. So now I have my grams per mole in this case. Now what I have to do is I have to look at what else I was given. And if you notice, the problem wants us to find the volume that 2 kilograms of methane gas is going to occupy. So my 2 kilograms, I need to convert that to grams. So 2 kilograms times 1,000 grams for every 1 kilogram is going to give me 2,000 grams. Now the reason I wanted to do that is because I need to start out, and I'm just going to slide this up here a little bit. There it goes. Okay, we have 2,000 kilograms that we're starting out with. So remember, we're going to list out what our beginning values. We found that the molar mass of methane gas was 16.043, and I see that I need, in order to cancel this grams out, the grams has to go on the bottom, so I have 16.043 grams here, and I have 1 mole up on top. So when I multiply and divide this out, I end up with 125 moles of methane gas. And then what I'm going to do is I'm going to take that 125 moles, and you could have kept going if you wanted to on this up above, but I'm going to take that 125 moles and I'm going to apply that conversion factor that said that we had 22.4 liters is equal to 1 mole. So again, I want my moles to cancel, which means my 1 mole is going to go on the bottom, and my 22.4 liters is going to go on the top. So by doing this now, my moles are going to cancel, and I have 125 times 22.4, which is 2,800 liters. And this right here is the volume that the 2,000 kilograms of methane gas is going to occupy at standard temperature and standard pressure. So this is going to lead us into what we call the ideal gas law. Now we've already talked about the combined gas law, which only dealt with Boyle's law, Charles's law, Gay-Lussac's law, and we combine all them together. When we want to talk about the element of the numbers of moles, or we're given a mass or something like that, this is where we have to incorporate another variable, which in this case is going to be N. Okay, you can see it right here. And we are going to come up with what we call the ideal gas law, which is PV equals nRT. So I would memorize PV equals nRT, and the P1V1 over T1 equals P2V2 over T2, or your combined gas law from the last video. And these are the two main equations that we're going to use. If your problem talks anything about the number of moles or a mass or anything like that, then you know that you're going to have to use this one. If it's lacking that information and you don't have to find it and it's not given, then you're probably going to use the combined gas law. But as you can see right here, P is still pressure, V is volume, N is the number of moles, R is this something that we call the ideal gas constant, which we'll talk about here in a second, and T is again our temperature in Kelvin. Now up top here you can see for the R value, we have R is equal to PV over NT. And they literally got that by taking this equation, so I have PV equals nRT, and if I want to get R by itself, I'm going to divide by the N and the T, and these are going to cancel, but I have to do that over here. So you can see then that R equals PV over NT. And again, this is nothing that I would memorize because I know that we can just manipulate the equation. But what we do need to know is the values that we're going to find on the next sheet. Now here's our table of values for R values. These are always going to be the case, okay? This is something that would be given to you like on a test or a quiz. I don't expect you to memorize these, but you can see there I have 3 different numbers here. And if you look over here, the units look all pretty much the same with the exception of one thing. If you look at, I have L, so I have my volume, if you look at the units, times a unit of pressure divided by N, which is the number of moles, times your temperature value. Okay, so this is your unit for R. It's volume times pressure divided by number of moles times temp. So the key difference between, or how you figure out when you have to know which number to use, is going to come down to what is your unit of pressure, because this is the only thing that's going to change. So let's take a look at an example to see how this is going to work. Example 6 says to calculate the number of moles in NH3 in a 3-liter vessel at 3 times 10 to the second Kelvin, or that's our temperature, and it's 300, with a pressure of 1.5 atmosphere. So if you notice, we have a volume, we have a temperature, and we have a pressure, and I'm looking for the number of moles. So because I see that I'm looking for something that deals with moles, I know that I'm going to have to use the PV equals nRT. And at this point in time, I'm looking to solve for my N value. So to do that, I'm going to adjust my equation right from the beginning. I'm going to divide by R and T. So what this gives me then is N equals PV divided by RT, and now all I have to do is plug in my numbers. So N is going to equal my pressure, which is P, or 1.5 atmosphere. My volume is going to be 3 liters. My R value, if you go back to that previous table that we looked at, we're going to actually use the unit that, or the one that uses atmosphere for the pressure, which is 0.0821, and that's liters times atmosphere divided by moles times Kelvin on the bottom. And then our temperature is going to be 300, which is 3 times 10 to the second. So I'm going to write in 300 Kelvin. And when we multiply and divide this all out, I get 0.8 moles. So there's 0.18 moles in NH3 in a 3-liter vessel at 300 Kelvin with a pressure of 1.5 atmosphere. For our final example, we're told to calculate temperature when N is 0.014 moles. We know our volume is 1.2 liters and our pressure is 0.988 atmosphere. So again, I'm given that I have an N value, so I know I'm going to use PV equals nRT. I need to calculate for T, so that means I'm going to go ahead and divide by my N and R. I'm going to do that on both sides. And let me change color here. So this is going to give me that T is equal to PV divided by nR. And I'm literally just going to plug my values in. So temperature is equal to pressure, which is 0.988 atmosphere. Volume is 1.2 liters. And I'm going to divide that by the number of moles, which is 0.014. And our R value, because my pressure is in atmosphere, my R value is going to be that 0.0821 liters times atmosphere divided by moles times Kelvin. So when we simplify, I end up with a temperature of 1031.5 Kelvin, which is really, I'm going to subtract 273 from that, 758.5 degrees Celsius. And that would be the temperature when all of these other parameters are set. Now, before we conclude this video, I do just want to kind of point out a few things between what a real gas would really do versus an ideal gas. You have to remember that when we're talking about the ideal gas, like model, that's exactly what it is it's just a model. This is supposed to be like used as a predictive tool, like what do we think is going to happen? So with any predictive tool, you always make a set of assumptions, and those set of assumptions follow the same set of assumptions that we talked about back in chapter 12 with the kinetic molecular theory. We assume that the particles are not taking up space, that there's no intermolecular forces going on in between the molecules, that nothing is going to be attracted to the walls of the container, particles are always going to be in a constant random motion and never stopping, and that they're going to follow the laws under conditions of temperature and pressure. So reality says no gas is truly ideal, okay? But if we're going to use a model, this is going to get us pretty close, at least to being able to predict some things. Some things to keep in mind, though, when you use this model is you have to realize that when we have extreme temperatures and pressures, our real gases are going to deviate from the ideal gas behaviors because of those extreme temperature and pressure changes. The polarity and size of particles is going to have an impact. Okay, we have some molecules that are polar, such as water vapor. So they are going to have large attractive forces versus some molecules that are nonpolar. Okay, large molecules are also going to occupy more volume, which is going to kind of deviate from that ideal gas law as well. Okay, so if we have the right conditions, then the ideal gas law is going to allow us to approximate or predict some type of a behavior. But you have to know that this is only an approximation, and the reality says that things aren't always going to go as planned. So on that note, if you guys have any questions, please don't hesitate to ask. Thanks and have a great day.